Good afternoon, everyone. Welcome to lecture 11 in this course of machine learning. This online session, we discuss the data pre-processing or dimension reduction or data cleaning. So this topic is very important in machine learning, as we will see at least few of the tools we use in order to improve the data quality for the learning process. I will just share the presentation. And as I'm always saying that I'm not going to go through them slide by slide, so I will skip some of them, but what is required from you in this course is recorded in the lecture. Okay, share. Okay, so in this data pre-processing, for example, if we look to this slide, it is written there that data quality is essential for good machine learning algorithms. And if we continue, it is almost the same, but with different colors, the same, but smaller scale, the same, but different color and oriented, and the same. Okay, so what we have seen now is the same slide, but it has been repeated in different ways. Unless there is some coding in this color, maybe there's some information, the color or in this orientation. But if there's no information there, it means that what we have is just like 3-4 slides contains the same information. So this loss of there is a redundancy here. So repeated data doesn't have or doesn't carry information. So data quality is very, very important. As I mentioned in the previous lectures, that garbage in is garbage out. It means that if you have no sense data, and no matter what the efficiency or the quality of the machine learning algorithm, if you train them with high biased or garbage data, the model that you will get is garbage. So in that sense, we have to pay attention about data. Data is very important, how to clean data and how to check the quality of data. The size of data is important in machine learning, but it is not as important as the quality of the data. You can generate, useless data like garbage or noisy data or no sense data. You can generate a lot. You can by like scientific data. So, but the information it carries is the important thing that we are looking for. So, in that sense, what kind of problems that it can be associated in data? We have different problems associated with data. First is related to the quality. If you have huge data but highly redundant, it means that you repeat different things. I give you one example. You are measuring the noise or let's say vibration of certain engine, okay? And then for that purpose, you use 2 sensors or 3 sensors or n sensors, doesn't matter. If the vibration of that engine is symmetric or is, let's say, homogeneous. It means that the same vibration is um, the same vibration pattern, exactly the same from different sensors in the engine. So now you bring me, let's say, 20 sensors measurements, but when I put them, I find only scaled difference because one of them is far away from the main source of the vibration and so on. So maybe with out of each sensor, you might have, let's say, like millions of information or of data, millions of samples, maybe hundreds of millions of samples over each sensor. But because they are repeated in the same way, maybe just scaling, okay, but in the same pattern, and you have 50 sensors, so in that case, you have a huge redundant. You cannot say that I have 50 data input. You cannot say that I have 50 features. You can say that I have a single feature. But you might add one information that the vibration is homogeneous over the whole like engine. Okay, this you can add this information from the different sensors that you have, but you don't need to use the same data because it is just the same data, just a scaling version. For example, the input sample here, the sample is 5, 4, 2, and the second one is 2.5, 2, and 1. It is just scaling. So in that case, it doesn't matter that you have a huge data if you have redundant data. You have a lot of the same data that you generate. Okay. It is the same that if you measure you take pictures, images and you want to distinguish between, let's say, orange and apple, for example, or between cats and dogs. Okay, so if you bring me, you say that, I have this file. In this file, I have 1 million picture. Okay, it looks very nice. 1 million picture, a lot of data. But when I check the pictures, I found it just one picture, but repeated million times. In this case, you can say that I have a single picture. You cannot say that I have million picture. It is just repeated, one single picture repeated. If the single picture is scaled down and up and oriented, maybe in this case it has information. Even if it was the same picture, but you don't need 1 million in this case. So redundancy is one of the problems in data. Okay, this is one thing. Biased data. So if data is biased already, if you want to learn or train something with the data, but the data was already biased somehow, either by the people who generate data, maybe intentionally or unintentionally, but it can be biased data. And if the bias of data is very large, this will be problem. It can be garbage data. What does the garbage data mean? If I asked you to give me file, for example, with the students' grades, I asked the university to give me the students' grades in certain course during the last 50 years. Someone who doesn't have such data, he or she came to the computer and then define the courses and then generate a random number between 0 to 50 or 200, because it is percentage. From 0 to 100, uniform distribution, random number generators, and then they give me Excel file with like anonymous names. There's no names there, but they claim this is student 1, student 2, up to student 10,000. But all data here was generated like randomly. So it is garbage data. So in that case, if you take this data, you thought that this data is real data, and you start to find information, all model, everything you get from this result is garbage. meaningless, useless, because the data itself was not real data, or was like garbage input. We have other problems. Sometimes we have data which quality data, good data, but it has been, for example, corrupted by some noise or some like bias. There's a bias, but not dominating bias, but it has some bias as well. So this is lower quality, but it can be useful in this case. Okay, you have other kind of data that it is mixed. You have real data there, you have but some of this data, you have high redundancy in that data. So how can we clean this kind of data? How can we improve the quality of this data? Okay. So we have different types of problems associated with data. One of the problems is that the structure of the data. Many times the data is unstructured, especially if you want to build a new machine learning algorithms, or you want to build some data event system based on AI algorithm, but a large part of your historical data was prepared in the time where there is no like intention to use AI. For example, if you go to one big like old company like ABB, for example, or Siemens, so they have a huge data, like huge documents based on their like engines and motors and systems they designed. And this like huge data was documented, many of them even by handwritten, and it was not structured. And even with the computerized or digitalized, but still it is not structured. They don't follow the same principle in preparing those documents. So you can see that when you have like thousands or tens of thousands or even hundreds of thousands of such documents scattered in different offices, and maybe scanned in different computers storages, and you want to collect this data and to build some structured way to put this information into, convert them into numbers, into structured data, structured input. This can actually consume a huge time. Okay, so we have many problems associated with data. And also one of the problems in data, that the attributes or the features, you know, that we want to build model, and we want this model to be trained over the input data, and the input data consisting of like features or attributes, and then the number of interests can be very large number of interests, and can be very large also dimension. The dimension here, when we say dimension, we mean the number of attributes. Out of this data, if you are interested in like certain feature, or you are interested to make a building or like prediction for, let's say, the prices, share prices, or in some economy or marketing, or maybe the predicted power like load, or the load, predicted load, or predicted power consumption for the coming weeks, and so on. So now you have data, you have features, and you don't know yet what are the features which can affect that much the result that you want to check. Okay, so of course in the beginning we try to collect as much possible as we can of features, and this is very important with the new AI and data event or data based systems, because many times we don't know the importance of certain feature. So some feature can be very critical and we don't know that. And this is especially important in medical science and in bioinformatics. So with people that they have certain diseases, uh, it is important to collect as much data as possible that we can have based on the daily like life habits or the features in the patient. Maybe also some information can be very important, if they have this disease in their, for example, kids or parents or grandparents. Going also to some genetic information can be very important. The city where they live is can be very important. So there are many different information can be also very important. Some of them, doctor, especially when we talk about like 30, 40 years, 20 years, where we don't have such like advanced AI-based systems. So some information maybe not used that important, or doctors they don't think that this is very important, but it can be like key point in some diseases. For example, where is the city exactly, or what is the village where this patient is. So this might reflect the quality of water there. Maybe this disease is related to some pollution in that area. So different information can be obtained by using as much as you can of features. However, large features as well, very large features, if some of them useless, at least for what you are looking for. This means that you need higher computation power for learning. And this might lead also to some kind of like redundancy in data, or it can many times even reduce the quality of learning because you have a huge attributes, but actually you don't need all these attributes in your learning. So what happened, this leads to using over complex system. For example, you're using over complex, and this will lead to like memorization and overfitting in your data. So um, we need as much features as possible, but the important features, not any feature. So now I will start today by talking about data reduction. So how to reduce data and unnecessary data, unnecessary dimensions. How can we remove them? Actually, we have two ways to do that. The first is called feature selection, and the second one is called feature extraction. Feature selection is related to how to reduce the number of features. For example, if for certain patient you have 100 feature, and now you are looking for certain disease, or the probability that this patient will cure during 5 years from this disease, okay, and then you check, do you need all these 100 feature? Maybe you need only 10 out of 100, maybe you need only 20. What are the most important features that will affect the information that we are looking for? Okay, this is called feature selection. The second type of data reduction is called feature extraction. In feature extraction, we don't actually remove any features, but what we do, we project the data that we have as input, we project them to smaller space. For example, if the data that you have, it has, let's say, 100 dimension, then by making projection of 100 dimension into 30 dimension, and now this 30 dimension, we can claim that it contains most of the information available in the 100 dimension. So I don't need to remove any feature. I don't need to drop any feature. All what I need is to make like a projection of the high dimension into smaller dimension. However, the new smaller dimension is not possible to be as like explainable as before. For example, assume that the data that you have is the patient weight, patient height is the second feature, patient weight, we said patient weight, maybe the BMI, then like blood pressure, blood sugar, maybe the heart rate, age, smoker or not, male or female. So we have these features now is readable. You can see them in Excel file clear. But when you make the projection, so what is the projection? The projection that we have a new feature now, and this feature is a weighting sum of the input features. Maybe zero point 0.1 of the age plus zero point 0.2 of the weight plus zero point 0.4 of the like blood pressure, blah, 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 blah. Then we get one number. And now this number representing those features. So now out of 8 features, I can project them into maybe 2 or 3 dimensions. Those 3 dimensions, they may save all information in the previous 8 features, but now I have 3. So I have easier learning, and I can always going back and forth from I mean, when you have the new patient with the new features, then you can just make a projection into the 3 like dimensions. Out of those 3 dimensions, I can see or I can decide if this patient has that disease or not. Okay, I will talk more about this in today online session. But let me check. I think there's question in the chat. Yes. Okay, this is private. Okay, we'll check this later after the lecture. Okay. Now, let me start by the feature selection. In the feature selection, data reduction, I have one of my PhD students. He was PhD student, now he's senior researcher in Helsinki University, but he was doing his PhD research in finding or building a model for certain type of cancer in medical science based on the features that they have. Now I don't remember exactly the number of features, but they were not that much, maybe 30 or 35 features. And then after learning process, when we complete the learning process, we got very good prediction because we divided, for example, if we have 70 patient or 80 patient, we use training for over 50 patient, and we validate over the rest 30. I think we had 300 patients at that time, yes. So the student did the training over maybe 200, and they use 100 for validation. And in the validation phase, the algorithm was able to predict the situation with very high accuracy. So we were happy about the result. But now the second question came to us that which ones of those 35 features are the most important in the prediction of the disease, of the cancer. Because doctors usually, some of this data needs time, needs money. For example, if you need some blood analysis, and this blood analysis, some of them, they are very expensive and time consuming. If we can say that this blood analysis is not important for this detection, then this is very important result, and this can be very also meaningful result of this machine learning. So we are not only building the algorithm which predicts, but also it can give us more like information that this blood analysis is not that important. And actually it was included to this because for some previous experiments, okay, and it becomes like part of classically that this blood should be there, the blood analysis should be there. However, we find that there is another analysis which hiddenly has this information. Okay, so by removing that analysis from the training, we found that the accuracy has not been changed that much. Almost we have the same detection accuracy. So this is a new result. And then we can think beyond that. Where is the analysis which include this one, or highly correlated to this one? However, in this feature selection, actually, we need to repeat many times the training. For example, we can, in the beginning, we make the training with all features that we have. Then over the validation, we found that the error over the validation, or let's say the accuracy in the validation was, let's say 90%. Okay, we are very happy for that. Okay, then what we do, the students came to the same data and then just repeat the whole training, but after removing one of the features. Just select any one of the features, remove it, make the training. Okay, after that, check the validation without that element or without that feature. Then we check the accuracy. We found that the accuracy dropped from 90% to be, let's say, 60%. Oh no. In this case, we say that that feature is important. Repeat that feature back and then remove the second feature, remove the third feature, and repeat and repeat and repeat until we remove one by one. Then we found finally one of those features are not important. Okay, is that enough? No. Now we need to again, but remove 2 by 2. Then come again, remove 3 by 3. So you can see that this process is very highly or very high, it needs very high computations and also time consuming, especially if you have very large dimensions. So if you have, like, let's say 100 dimension, okay, and you can see now how many trials that you want to do. It can be trillions of trials because you take one by one, then two by two, but even the two you take, they are different than 3 by 3. So you can see that how many like combinations that you have. However, it is straightforward. Okay. The second one is the feature extraction. Feature extraction, as I said, that it works by projection. And the nice thing with the feature extraction, especially in the PCA, the principal component analysis, that it is unsupervised. What it means, unsupervised? It means that you don't need actually to do any kind of machine learning, not like in the feature selection that we are applying the machine learning with the data. But with the PCA, before doing any machine learning algorithms, we can clean our data. We don't care about, is it data for regression? Is it data for classification? Is it data for clustering? We don't care. We take just the whole data, we make the PCA, we improve the quality, then we can, after that, we go to the machine learning algorithms. And also we have another version of projection, but this works with the supervised learning. Is called linear discriminant analysis, LDA. So those are the most important and the most basic and the most important techniques in the data reduction. And by the way, those two techniques, you can say that they are statistical tools more than machine learning tools. They are statistical tools, especially the principal component analysis is one of the oldest statistical tools applied in statistics, and still today is one very strong and very like fundamental technique in data reduction and data analysis. Okay. What was explained in the lecture is the subset selection, and you can read. We have two kinds of subset selection, as I mentioned at the beginning. We have forward selection, which means that you start with no features and you start feature by feature. You put the first feature, you make the learning, you check the quality over the validation, you take the second feature and repeat, third feature, repeat until D features. Then you start to take by two features, then you start to take by three features, and so on, and you repeat until you get the acceptable validation accuracy. The second one is the backward selection. This is what my student did, that you start with all, you know what is the best result that you have, then you can remove one by one until you reduce your data. So there's some explanation in the slides, so you can read them. And also I put some examples that you can use my neural network function. You can use them to find this result. Then the important, also very important part of the projection. So the projection, the most important is the principal component analysis, PCA. So the PCA, the idea of the PCA is very simple, but the result is amazing. The idea that here, what is X here? X is the data that you have. So I have in entries, in patient, in engines, whatever was in is the entries, okay? And then we have D is the dimensions. So X consisting of in rows, okay, and D dimension, D columns. D is the dimension. D is the dimension or the number of features, the number of attributes. This is X, okay? Now, my idea is that I want to project all this Excel file, all this data that I have, I want to project them with weight vector. You can see this is the weight vector, W transpose. W is D by 1. It means that W transpose is 1 by D. Okay, so now I project all this data into this weight, and then I get this vector. This vector will be 1 by n. So it will be like one entry from 1 up to n. Okay, and this vector, it likes you have representing all data that you have, which is n by d. You represent them as a one vector with d dimension. I repeat, because this is important, is what is coming to explanation in the coming analysis of this PCA. Assume you have 1,000 patient. Okay, I have 1,000 patient in my Excel file, and for each patient I have 50 attributes, 50 features for each patient. So I have 50 and I have 1,000. So now you have a matrix. This matrix is 1,000 row times 50 columns. Okay, I can project all this matrix 50 by 1,000 by 50. I can project them with a vector, and this vector is only the dimension of this vector is the same as the dimension of the matrix. So because I have 50 features, So the vector, this vector W, is the length is also 50. When you make this multiplication, you can see multiplication W transpose, it becomes 1 times D. D here is 50, and this will be 50 times 1000. So Z will be 1 times 1000. It means that it will be one vector, and this vector, it has 1000 element. Okay, what's the meaning of 1000? Thousands here is the number of patients that we have in the file. So I have 1000 patients, but now instead of representing each patient with 50 features, now I am representing each patient with only one feature. Okay, what is this feature? This feature is a linear combination of all 50 features. Okay, then you ask me, what is the criteria of selecting this single feature? Of course, I will not be satisfied with a single feature. I show you later how to add the second vector and the third vector, and they call like the principal components. Now this is the first principal component. The first principal component is the number of patients, but it is a single element. They said this single element should contain as much as information as possible from the matrix that you have. You have 1000 by 50. It has information there. Now, each element now should contain the highest possible information of that patient. Okay, but how can I measure the highest principal information or the highest information? If the data is in general, this is in general, okay? In general, the differential entropy, I don't want to take you to the information theory, but in general, the entropy or the differential entropy, the measure of the information usually is increasing function in the covariance matrix of the data in general. Covariance matrix. So in other words, the data which has the highest variance, it should contain the highest information. I give you example. I want to make things easy, at least because mathematics is easy. As you can see, mathematics, you can do it, especially if you have good background in linear algebra. So you can repeat the calculations in front of us now very easily. But I want you to go deeper, not only to solve mathematically the problem, but to understand why it was in this case. Assume that if you have, after this projection, you have the vector, okay, and that vector that you get, all of them contains the same number. Like let's say 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. All the 1000 patients, they have exactly the same number. How can we differentiate between patients here? Nothing. No information. No information. All patients have the same number. No information here. Okay? Let us take not this very extreme case, but let us take another case. The first patient, the number, it was 1. The second one was 1.2. The third one was 0.9, 0.95, 1.05, 1.3, 0.85. So all patients, they are different, but the numbers are very close. Still, the information content in this vector is not that much. There is some information, but very little. Okay. Let us now take this case. The Z vector that we get for the first patient, it was, let's say, -4. The second patient was 0. The third patient was 80. The fourth patient was 60. The fifth patient was minus 75. Now we have big differences. Big differences, what it means? It means that those patients, there are some differentiations between them, and this vector representing these differentiations between them clearly. Okay, so that differences, how can we measure them? We can measure those differences by variance. Variance gives us the differences between the entries. Of course, we can after that normalize them. So we can subtract the mean just to normalize, but still now the variance representing the differences between users or between inputs, between entries. So in that case, our purpose is to maximize the variance. Maximize the variance. So we are looking for what? We are looking for the optimum W. We are looking for the optimal vector, weight vector. What is the optimal weight vector which maximize the variance of what? The variance of Z. Let me have the laser pointer. So I am looking the optimum W that maximize the variance of the vector Z. How to do that? It is easy. Simply, we can calculate the covariance of X. The covariance, because X now we don't say variance. X we say covariance. Why? Because X is a matrix. And the matrix we studied before, we showed before, previous lecture and the lecture before that, we show what is the covariance of X is the expectation of X minus X mean times the X minus X mean transpose and these things. So now we calculate the covariance of X and we call it as Z. Okay. We have this Z1. What is the variance of Z1? The variance of Z1 is, as we know, that we take the Z1 minus Z1, the mean of Z1, okay? And it will be multiplied by Z1 minus the mean of Z1 transpose. And then we got the variance of Z1. And the variance of Z1 in this case will be nothing, but it will be W transpose times the covariance is Z times W1. We can easily prove this if you go back to the second lecture and the previous lectures. Okay, so now this is the variance. My purpose is to maximize the variance. But if you want to just maximize this variance, because W1 is just weight, W1 is just weight. So in this case, this weight can go to infinity. Remember, and I mentioned this also in the previous lectures, every weight, every vector, it has magnitude and direction. Okay, now I am looking for the direction of W, not it is magnitude. The magnitude, it doesn't matter. I am not looking for the magnitude. The magnitude can be anything, not zero, because zero is trivial in this case, but anything not zero. But I am looking mainly for the direction of W. Because of that, to avoid the case that W can grow to and diverge to infinity, I put here the magnitude of W1 equal to 1. So this will be like concentrate. What is the optimum W? Where it is magnitude is 1, but what is the elements of W which makes the variance maximum? Why we make the variance maximum? Because I maximize the information is extracted from the matrix X. So this is the case. So now to maximize it, so I maximize W1. I call it W1. It was here W, but we call W1 because this is the first component. This is the first component. So maximize W1 transpose phi Z or Z W1. Then by using Lagrange multiplier, please go to part 1 in this course, We explain this minus alpha or gamma, you can call them whatever you want, whatever you want. W1 transpose times W1 is what? Is actually the magnitude. This is the magnitude. The magnitude of any vector, you take the transpose times the vector. It will be scalar in this case. So I subtracted from 1 because this is the constraint of this optimization problem. And now I want to maximize this equation, this Lagrange multiplier equation or Lagrange problem. I differentiate this with W1 because W1 is the element that I am looking for. We differentiate with W1 and set it to 0. And then I got this result. 2z W1 minus 2 alpha W1 equal to 0. If you take this to the other side, you cancel 2 with 2. So what we get? We get z W1 equal to alpha is a scalar times W1. If you have principles of linear algebra, you will know now that alpha is eigenvalue of z and W1 is eigenvector of z. Z is the covariance matrix of X. Okay, so now we have that alpha is the eigenvalue of z and W1 is the eigenvector of z. But which one? If you have matrix, let's say the dimension d by d, as I said in the case of patients that I have 1,000 patients and I have 50 dimensions, so z here will be 50 by 50. 50 by 50 means simply that you will have 50 eigenvalues and 50 eigenvectors. And because this z or this covariance matrix is symmetric, so all these eigenvectors will be orthogonal to each other. But which one now I should select? Which W1 I should select? I have 50 different eigenvectors. Which one representing the one which preserve the maximum variance or the maximum information from data? To know this result, to know what is this, we can substitute simply. We know that this W1z, if you multiply here by W1 transpose in this way, what you will get? You will get W1 transpose Z W1 equal to W1 transpose times W1 is equal to 1. This equal to alpha. You can see this will be equal to alpha because this equal to 1. Okay, this equal to alpha. Okay, what is this? If we go back, actually, this is what we want to maximize. We are looking to maximize the variance. So it means that we want to maximize this one, then we want to maximize the eigenvector, the eigenvalue. We want to maximize the eigenvalue. Then the solution of this problem is that alpha is the maximum eigenvalue of the matrix Z, and W1 is the associated eigenvector with this eigenvalue. It will be simply like that. So now we solve the problem. Now we solve for the first principal component. The first principal component, W1, is nothing but the eigenvector of the covariance matrix associated with the highest or the largest eigenvalue. Okay, now we found the first component. But as I said, the first component might not be enough. You have 50 features. You have 50 features. So now let us go to find the second component. What is the second component? We will do the same way. We define Z2 equal to W2 transpose times X transpose. Okay. However, if you solve only this one, you will simply get the first one. You have to add another constraint in your optimization. The other constraint that W2 must be not W1, must be different than W1. So in that case, because all eigenvectors are orthogonal, so W2 must be orthogonal to W1. What is the meaning of orthogonality? It means that W2 transpose times W1 should be 0. So this is what we did here. So now we extend a little bit our optimization problem. Now it is maximization for W2 now. And I maximize the same function as before, but now we use W2, the second component, the second principal component, minus I will keep also the the magnitude or the length of W2 equal to 1. Okay, this is the second constraint as we did in the first constraint as or the first component. And now I added this one. This one, it means that W2 must be orthogonal to W1. So W2 transpose times W1 should be orthogonal. So, and this is our second Lagrange multiplier beta. Okay. And after solving this in the same way, after solving this, we got very interesting result. We got that W, this W is, sorry, ZW2 is equal to alpha W2. And you need the same, in the same way, you need to maximize this one. So if you multiply here by W2 transpose and you multiply here W2 transpose times W2 equal to 1, then I want to maximize this one. Then the result simply that alpha will be the second highest eigenvalue. And W2 is the eigenvector of matrix Z, which is associated with the second highest eigenvalue of this matrix. So we calculate the first component is the eigenvector associated with the highest eigenvalue. The second component is the eigenvector associated with the second, the first one with the highest, the second one with the second highest eigenvalue. The third component, the third principal component, is the eigenvector of matrix Z, which is associated with the third highest eigenvalue of that matrix. So in this way, we can start calculate or collecting the principal component in this way. When you should stop? Okay, we calculate the first, we calculate the second, we calculate the third. Okay, in the example of the patients with 50 principal components, if every feature, every attribute in that patient is very important, is extremely important, everyone has the same importance, with very important, you cannot ignore any of them. Of course, this is very extreme case, by the way. This is not the case in most of real problems, but let us assume this extreme case. You will get 50 components in this case. You will get 50 principal components. The number of principal components will be as the same as the number of features itself. So in that case, principal component is not working. It cannot reduce the data because all eigenvalues will be high, large. All eigenvalues, maybe this not the same large. Maybe, for example, the highest one, let's say, equal to 30. Next one is 29. Third one maybe 26. The fourth one maybe 20. The next one is 19.99. The fourth one. So all of them, they are large values, which, because the importance of the eigenvector or the importance of the principal component representing by the value of the eigenvalue, how large the eigenvalue. If you have eigenvalue equal to 0, it means that component doesn't have any information. You can, so for example, assume now that out of these 50 features, I got W1 equal to 23, W2, W3, W4, up to W20. Up to W20, they have like large values. I will explain later or I will mention later how can we say it is large or not. I will mention this later. But assume that the first 20 eigenvalues are large enough, and after 20, lambda 21, 22, up to 50, all of them are zero. All of them are zero. What it means? In this case, it means simply that out of 50 features that you have, there are intercorrelation between the features, highly intercorrelation between the features, in the way that we can reduce them into only 20 dimension, and we can ignore the other 30. But there is a mistake. Many students do it. They thought when I said 20 dimension, it means that I will take the first 20 attributes or the first 20 features. No, this is wrong. Those 20 features, or the new dimension with the 20 features, every feature is a linear combination of the 50 features, the original 50 features. So you have to remember this. Every feature of those 20 is a linear combination of the previous or the original 50 ones. So you cannot simply drop the original features, but you can project them into that new 20-dimensional problem. Instead of 50, now I use 20. Those 20 are very highly independent. Every element has information. So that there is no redundancy. The redundancy is at its least possible number in this new 20 dimensions. Okay, so now we are able to reduce from 50 up to only 20. Sometimes we don't have zero, actually. We don't have zero, but we have small numbers. For example, in this 50 case, I have, let's say, the first 20 eigenvalues have considerable number, but the last 30, they have small numbers, comparably small numbers. A small number means low information. For example, if you have one of them is 20, the eigenvalue is 20. Other one, the eigenvalue is 0.1. So 0.1 indicates that it has much, much, much lower information than that 21. And sometimes those low eigenvalues entries are because of noise. So removing them can improve actually the machine learning algorithms, can improve the features, can improve the classification, improve the regression by removing the very low eigenvalues features from the calculations. So again, I repeat, in the beginning, you have the matrix X. This is the original data. We calculate the first component, the second component, the third component, and so on. And the first component is associated with the highest eigenvalue, the second highest eigenvalue, the third highest eigenvalue. And one way that you can say, you can use, of course, because when you remove non-zero eigenvalues, you can improve, actually, as I said, because you are removing noise, but also you can sacrifice some small information. Yes, the information is small, but sometimes can be somehow affecting the result. So you need to be as an expert, data expert or data analytics, you need to define what is the lambda, what is the eigenvalue, where after that I can just ignore and remove. One of the techniques that I wanted to mention, they remove the data which has less than the average eigen values. You know, you can take the summation of eigenvalues, and the summation of eigenvalues is the same as the summation of the trace of the matrix. The trace of this Z matrix, you know that the matrix is D by D. So the diagonal has D element. So if you add the diagonal elements, all of them, the result will be the same as you adding all eigenvalues of this matrix. So they take the average. So they take the summation, divide by the number. For example, if the summation is equal to, let's say, of the eigenvalues is equal to, let's say, 100, and the dimension is 50, so 100 divided by 50 is equal to 2. Then you decide to take the highest eigenvalue, the second highest eigenvalue, the third, the fourth, and until you reach to number of eigenvalue is greater than the average, greater than 2, greater than or equal to 2. You take all of them, and then you ignore what is less than 2. You remove them. Okay, so for example, if you have 50 dimension, maybe you can, in this case, you can reduce it to, let's say, to 20 dimension, or only to 10 dimension. Okay, so this is the way how the principal component analysis is working. So the idea is there. Let me okay, now just explanation how to do it, but maybe I can go to the white screen, and also let me okay. By the way, the principal component analysis sometimes can be very, very useful, especially in data recognition, in voice recognition, in image recognition, because it can reduce the data hugely. You can sometimes the dimension of the data that you have, like millions, and then you can reduce them to 20 or 30. So this is very important. But I just take some simple example of these 50 users. But let's say that you have this data, okay? I just show you what you are doing, what we are doing here. Remember that the principal component analysis is unsupervised, which means that you don't need to show the result. So you don't know the class, you don't know anything. So just you have data in this way. Okay. I will take the example of the patients. So I have here 1000, and I have here dimensions is 50. Okay. Now I take one by one. So I first of all, this is X matrix. Okay. I compute the covariance matrix of it. So the covariance will be 50 by 50. This is the covariance. Okay. Then as I explained now and approved as well, we found that we can calculate the weights that the principal components given as the weights, and the weights is actually 1 by 50. Okay, this is the weights, 1 by 50. Okay, so now I calculate the first weight, the second weight, the second component, and blah 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 until we say K component. Okay, now if this is the weight, if you multiply, this is element. How many element here? We have 50. Okay, so 50 by 1 times 1 by 50. So if you multiply each patient here with this weight, out of 50 we get one number. So now after this multiplication, vector multiplication, I get only one number. This one vector, which is actually has the same, it will have 1000 element, but it will be only one component, one feature. This one representing the highest eigenvector or the eigenvalue of the Z matrix. This is the maximum. And in this case, this first vector contains the highest information from all this matrix. Then with the W2, I do the same with W2, which is the eigenvector associated with the second highest eigenvalue. Then I calculate the second element, then the third element, then the fourth element, and so on. Assume that now I found that I take until certain W, which representing that I should have only 10 elements out of 50. So I have one dimension, the second dimension, until the 10th dimension. Okay. So I have now this new matrix. The original matrix is 1000 by 50. The second matrix now, or the reduced matrix, is 1000 by 10. 1000 by 10. Now I can use this new matrix in our machine learning algorithm. Okay, for example, if we use them for let's say clustering, for example, then I can use this new data for the clustering, because I still know this is patient 1, patient 2, patient 3. However, the dimensions now is not anymore directly the attributes, but every one of those is a linear combination of these original attributes. Now I use machine learning, and then I get the result. Okay, I made the validation. For example, out of 1000, maybe I take 700 for training, 300 for validation. My machine learning algorithm now is working fine. Okay, we are happy with our machine learning now. Okay, our machine learning now, it has only 10 inputs out of 50 as before, because those are the attributes. Now we have a new patient came, and this patient has, of course, his own 50 attributes. As we said before, maybe age, maybe height, weight, blood pressure, and blah, 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 blah. So we have 50 of a new patient now. What you should do now, you cannot take the new patient to the machine learning directly, because now we have a new dimension. We have only 10. So what you should do, the first thing, you multiply this new patient with W1, because this new patient now, for example, it is 1 by 50. You multiply it by the vector 1, which is 50 by 1. As you know from linear algebra, when you multiply row vector by column vector, you will get scalar. So this will be the first element. The second element is the new data with the W2. So you multiply by W2. This will be the second element. The third element with W3, the fourth element with W4, until the 10th element with the W10. Then we have now the new representation of the new patient, and then we can see how the machine learning will respond to the new patient. They can classify them, one of those classes, for example, we are looking for. So it simply work in this way. So this is very effective and very interesting algorithm. And as I said, it is very highly it is applied in statistics, applied in economy, applied in engineering, almost applied everywhere. And this is also a essential part in our machine learning algorithms. There is some debate. Is it intelligent method or not? Some say it is not intelligent. You cannot consider it as AI because it is just a statistical method. But some others claim that every AI can be explained as a statistical method. However, this question. Okay, so however, the principal component analysis, which has this capability, sometimes if the features is the frequency components in voice, and just think if you have like like 10,000 frequency component here. And out of this 10,000 frequency component, the PCA reduced them into only 50. One of the machine learning scientists said, if this is not intelligence, how can we say that any other algorithm is AI? So that scientist, he believed that PCA is also intelligent method because it can reduce thousands of dimensions into very small number, and still it can contain up to 95% of the information in the original 10,000 elements. So it is very, very important. And I think that this is enough for this. Sorry, I can. Um, just a minute. My mistake, stop the sharing. Yeah. So now this is about the principal component analysis, and then I gave some examples, some numerical example, and also I show to you how to solve it. Okay. And also there's another methods, especially when you have huge data. So you don't need to compute the covariance matrix. Sometimes the covariance matrix can be like headache, especially if you have data with like thousands of dimensions. So it will be a really, really big problem. But there are some other methods also. We can reconstruct the PCA components from those. Those was explained, most of them, in the recorded lecture. And also finally, the linear discriminant analysis is actually very straightforward. It is much easier than the principal component analysis. It is based on what is known as Fisher information, but it is also the principle here that we it is in the same way, but instead of making in PCA, we had different like principles. We take the data into like k number of dimensions. Here, no. Here they convert it into just one number. So every features, 50 features, for example, in the case of the medical data. So you have 50 features. You project this 50 into a single number. Okay, into a single number. But which number that you projected to? In this case, we need to know the classes. We need to know the class. It is not like BCA. In BCA is unsupervised. It doesn't matter what is the classes. Here you need the class. Here it is supervised learning. So you need to know the classes. So the idea how to find, I can draw it here. Maybe, okay, let me go again to the white screen. So now the principle is like that. I will go to the same example that I showed before. Okay. Okay. So we have 50 users. Okay. And for this 50, you have here 50 attributes, and you have 1,000 patients. And this is important, we know the result. So we know that the classes, if we assume that we have two classes, that this guy has that disease or not, so positive or negative. So we have this guy is maybe positive, he has the disease, this guy has positive, this one is negative, this one is positive, this one is negative, negative, positive, negative, and so on. So we know the result. So we have two classes, C1 or C2. Okay. If you want now to calculate based on this 50, I want to make a projection. So again, I will use weight W1. This W1 will be also, the dimension will be 1 by 50, the same way, 1 by 50. Okay. But what is the principle? How I select W1? I want to select W1 in the way that, because I have only two components, either C1 or C2. I want, when I made a projection, for example, C1 is the positive, C1 is the negative, okay? I want, when I make the projective for the first one to be, for example, here, and for the second one is positive, I want, because all positive, I want them to be as close as to each other, very close. What is the meaning very close? How can mathematically say very close? Means that minimizing the variance. I want, remember previously I was maximizing the variance. Now I want W1 to work in the way that it minimize the variance between the same class. For example, for this is a class 2. Also, I want them to be very close to each other, very close to each other. So minimize the variance of S2 and minimize the variance of S1. This is one task. The second task is to maximize the difference between the mean of each class, because here we have the mean M1 and we have the mean M2. Okay, I want to keep the means of between the both classes to be as large as possible, as large as possible. So this is the two tasks of computing W1. I want to select what is the optimum W1, which makes the variance within each class very close to each other, but the difference between the classes is as large as possible. And in the same way, because W1 can go to infinity, so in this case, I want also to keep the magnitude of W1 to be 1. So I want just to keep it 1 or 2, but fixed number. But I want to keep the distance as much as possible. So this is the principle behind calculation of W1. This is simply in this way. It is very simple principle, okay? And it is even much easier than the PCA. So in this case, how can we do that? We can do it by maximizing this function. You can see the maximizing this function. This function is M1 minus M2, the mean of each class. This is the mean of class 1, the mean of class 2. I want to keep them as large as possible, but in the same time, I want to keep the variance of each class within itself to be as small as possible. So when you divide a large number by very small number, then this criteria will be very large. And now I want to maximize based on W. So this is called the linear discriminant analysis, and it is very widely used in image recognition, for example. If you want to recognize like an image, is this person is me or not, for example, when you want to open your mobile with your picture. Okay, so that's it for today. I think now we gave in details the principles of at least two discriminant functions or two reduction functions. Okay, and okay, so the floor is yours now. If you have any questions, you can ask. This lecture, as I said, is important, especially for those who want to continue in machine learning. You need to spend some time cleaning your data. So this is important. And actually, we have more, not only those cleaning techniques in your data, but I just gave the principles for those, and we have some others, for example, this using encoder and decoder, but we can also explain them later when we talk about generative AI. Yes. If there's questions, please, you can ask Tahmid.
Yes, I actually had a question regarding the report, the optional report that you mentioned, and I just wanted to know, like, is there a specific structure that we need to follow, or is there like a specific kind of topic that we need to choose,
Yeah.
and if there's like a word limit or a referencing style?
Okay. Okay. Um, um,